Okay, let's take a look at free fall on page 2 in your two-dimensional motion packet. This would be the left-hand side of that page. Alright, so you can see the answer to this first one's 40, but let's see how we got there. So Ant Mini gives us $10 per second for 4 seconds. That'd be pretty sweet, especially if that was something that continued for a while. But how much money do you have after 4 seconds? So hopefully this is a fairly straightforward problem for you. We've got $10, that's where this is coming from, and we get that $10 for every 4 seconds, so times 4 seconds, and that gives us our total. Okay, moving on to the next one. So a ball's dropped from rest, picks up speed at 10 meters per second. After it falls for 4 seconds, how fast is it going? Pretty much the same problem as before, except now we're putting this in more physics terms. So the 10 meters per second goes there, and it's going for 4 seconds. So that's where I ended up with that. So I get a total of 40 meters per second in the end. Alright, moving on to the next. So we've got $20. Uncle Harry gives us $10 each second for 3 seconds. How much money do we have after 3 seconds? So we've got $20 to start with. That's where this is coming from. And then it tells us that we're given $10 each second for 3 seconds. So $10 a second for 3 seconds. So that would give us 30 here. We're already at 20 over there. Add the two together, and that's how I end up with my 50. And obviously I'm going fairly quick, but feel free to pause the video at any time, rewind it, slow it down. YouTube's got a feature where you can decrease the speed, increase the speed, whatever you need to do. All right, let's move on to the next one. So a ball's being thrown straight down with an initial speed of 20 meters per second. So that's our initial. And then it tells us after 3 seconds, how fast is it going? Well, we're assuming that gravity, it told us on this page, was 10 meters per second squared in terms of its pull. So it's pulling down at an additional 10 meters per second every single second. This being 3 seconds, 10 times 3 gives us a total of 30. Right there, we already had the 20 from before. Right, we add those two together, and that's where we end up with our 50. So again, pretty much the same exact problem as before, except now in more physics speak. All right, so let's take a look at number 5 here. You've got $50, and you want to pay Ant Mini $10 per second. When will your money run out? Well, if you've got $50 and you end up paying her $10 for every second, hopefully you can probably do this in your head, but if we want to put it into a mathematical expression, it would be, well, $50 to start with divided by $10 leaves us with 5 seconds. All right, next one, number 6. You shoot an arrow straight up at 50 meters per second. When will it run out of speed? So basically what we've got going on is we shoot an arrow straight up, and we want to know when does it get to that point right at the top here. All right, because that's when it's going to run out of speed, right? It has to hit 0 before it can turn around and end up going back down. So we've got 50 meters per second to begin with. We're losing 10 meters per second, or 10 meters per second of speed every second that we're going. So pretty much identical to the problem before, except now we're putting it in more physics terms. So after the first second, I'd be at 40 meters per second. After this next second, I'd be at 30. The next second, I'd be at 20. Then I'd be at 10. And then I'd be at 0. So we could also count it up and say, well, it took 1, 2, 3, 4, 5 seconds until I got to 0. Or throw it into our math. But here's how the concept would match up with it. All right, number 7. So what will be the arrow's speed be 5 seconds after you shoot it. So that's really bad grammar, right? So what's the arrow speed going to be 5 seconds after we shoot it? And again, kind of going up to the previous problem there. If I'm at the very top at the end of 5 seconds after its speed has run out, well, then it's going to be at 0 meters per second. Right? It's going to be high up there. But for a very split moment in time, it's going to be at 0 meters per second. This is something that's kind of hard for students to understand, because it seems like, well, how the heck can I possibly be at 0 meters per second here if I'm in the air? Well, think about it. If it wasn't at 0 meters per second just for a fraction of a second here, that would mean that the arrow's trajectory would go up the entire time, right? And it would never come back. And that's how it would end up getting into orbit, basically. So it has to be at 0 in order to come back. So at the end of 5 seconds, we'd be at 0. All right, so let's take a look at number 8. What will its speed be 6 seconds after we shoot it? What about 7 seconds after we shoot it? So I kind of drew in a diagram here to kind of help us out with that. We know that we would be at 0 meters per second after 5 seconds if we started at 50 meters per second, because we're losing 10 meters per second every single second that we're in the air. But then, after I've gotten a 0, now I'm going to end up coming back down. Well, at 6 seconds, that's really 1 second from the top. So I would have picked up 10 meters per second for every second. Well, if this is only 1 second right here, I would have picked up my 10 meters per second. And again, that's coming from gravity. In this page, it tells us to round it off to negative 10 meters per second squared. In reality, it should be negative 9.8 meters per second squared, but we'll get into that in future pages. Just don't let that throw you. We're just rounding in this case. So then at the end of 20 seconds, essentially we'd be 2 seconds from the top. It would be falling for 2 seconds. So that means, well, the first second it's at 10 seconds. The next second it's an additional 10 meters per second. So that means total of 20 meters per second on the way down. All right. Hope that helps.